Right guys, straight back into it. I don't want to waste time with a long intro here. We developed the aircraft equations of motion for translational motion. So we've got our x, y and z equations. We've got the left hand side. This was built up from taking the absolute velocity vector. The absolute velocity vector is u, v and w. And we put it into our Coriolis vector, or our first order Coriolis identity, and we get these terms here, and then the mass is just the aircraft mass. So this left hand side of things is m a absolute, and then the right hand side is our aerodynamic forces, sorry, not just aerodynamic forces, it's the non-conservative forces. So we've got the gravitational force, now these are all in body axes, the aerodynamic force, and we've got the propulsive force. So we use the Newtonian framework to build this up, and we're going to do the exact same thing for rotational motion now. So we'd like to do the same thing for rotational motion. Newton's second law, as we described it for linear motion, we would say the rate of change of linear momentum, let's just say momentum flux. The rate of momentum flux is equal to applied force. Okay, so for us, that's the A absolute is equal to the sum of the applied forces. This is Newton's second law for linear motion. For angular motion, for rotational motion, you may not have necessarily seen it expressed in a way like this. So the way that we will apply it is the rate of change of the angular momentum is equal to the sum of applied moments. Okay, so this left hand side is again, this is for rotation now. The left hand side is the rate of change of angular motion, sorry, of angular momentum. And then this right hand side is the applied moments. Right hand side is going to be a lot easier to get for this one. And the left hand, well, we know that it's just going to be equal to our applied total moments, L, M and N. The left hand side is going to be the one we're going to spend a bit of time going for, I guess. So this bit here, the fact that we see that it's an absolute quantity, we know, or we should sort of intuit by now, that we're going to have to use the Coriolis, first order Coriolis identity. So we're going to end up saying dH on dt abs is equal to dH on dt oxyz plus the cross product of the angular rotation vector multiplied by h. So we need to figure out whatever this h term is. So h is our angular momentum vector. Angular momentum sometimes has different symbols in physics, but we're going to stick with h for aerospace because that's what helps us in the subject. So the angular momentum vector, how do we get angular momentum? Well, it's related to the linear momentum and the distance away from the center of rotation. Okay, so we've got three things here. Angular momentum, distance away from rotation, and then here we've got our linear momentum. So linear momentum is just the product of the mass and this part here, the absolute velocity. So we're going to try and figure out a formulation that's going to help us determine the angular momentum contained within an aircraft, and then we're going to, once we get this h vector, we're going to put it into here, and this is going to give us the absolute, sorry, we're not going to put it into there, I think it's the wrong one, we're going to put it into here, and this is going to give us the time rate of change of the angular momentum vector in the absolute reference frame, or in the inertially fixed reference frame, and then we're going to make it equal to the applied moment. So that's how we're going to do this, and it's how we're going to build up the aircraft equations of motion for rotation. So we can sort of see the steps that we've got to take. Well, firstly, we've got to get linear momentum. We're then going to work out the angular momentum because of that, and then we're going to differentiate it. And then once we differentiate it, we'll have an expression we can then put into here. That's going to be the first differential here. And then we do the cross product of the second part, add them together, we get the absolute time rate of change of the angular momentum, and we're sort of on our way there. So angular momentum is it's the product of rotation and the moment of inertia. And we've already sort of got the idea of this moment of inertia because we covered it in aerostructures. So it's a product not just of the mass that is contained within an object, but how it's distributed within an object. So what we're going to do, we're going to split our aircraft up into lots of small pieces and look at the contribution of a single small piece of this mass towards angular momentum, and then we'll just add them all up, which is a fancy way, well, integrating is just a fancy way of adding up, so we're going to do that. So let's draw an aircraft. X, Y, and Z axes, and we're going to look at a small mass at an arbitrary location on the aircraft somewhere. So I've got this small mass which I call dn, and we're going to say that this exists at some location. Pretend that was a straight line. In fact, let's draw that with another colour pen so it doesn't look like an axis. Let's draw this on here. So that exists at location r dm, which is equal to x dm, y dm, z dm, and it's the elemental mass dm. So we are considering a small arbitrary mass at an arbitrary location on the aircraft. Because if we can work out how this contributes to the total angular momentum of the aircraft, we can then, we've done everything, because we can just repeat this time and time again, and ultimately we're just going to integrate it, and that is how we work out the total momentum. So we've got this small arbitrary mass that exists somewhere on the aircraft, and it's at this position rdm. So the aircraft is flying along. It's got the absolute velocity vector. So we've got u, v, w, and then we've got the aircraft body rate. So we've got p, q, and r. Okay, so we've got the body angular rates as well. So the absolute time rate of change of this part here, or the velocity that we can get of this component here, is going to be the product of the sorry, it's not going to be product. We're going to use the Coriolis identity to give the angular to get the linear momentum of this due to aircraft rotation. So we're only interested in any added momentum due to aircraft body rotations due to this rotation vector P, Q, and R, because any translation has already been included in the original equations of motion. So we can get this from the first order Coriolis identity. So just remember that we've got d of anything dt in the absolute reference frame is equal to d on dt in the local reference frame plus the cross product of the rotation vector and whatever vector we've got. So if we put in our position vector, which is defined in the aircraft body axes, then what we're going to get out, we'll get out the absolute velocity vector of the mass dm due to aircraft rotation. In here, we're going to put RDM. So D RDM on dt is equal to dr dm on dt oxyz plus the cross product, so it's I JK, PQR, and then we've got the three components. We've got X dm, Y dm, and Z dm. Okay, so let's do these. So the first time derivative, so we're looking at the first term now, we've got a column vector, X dot dm, Y dot dm, Z.dm. And then the cross product, so we're going to have three parts. The first one's going to be Z dm Q minus Y dm R. Second one's going to be X dm R minus Z dm P. And then we're going to have y dm p minus x dm q. Okay, so this is the absolute velocity, or the absolute translational velocity of this mass dm due to aircraft rotation. Now, all of these terms here go to 0 because remember, x, y, and z is the location of this mass in the aircraft axes, and we're assuming that we have a rigid aircraft. So let's put this here. Okay, if we can't assume we've got a rigid aircraft, then we're into the realm of aeroelasticity, where we have to look at the interrelation of structural deformation and aerodynamic forces, well, the change of aerodynamic forces due to the change of shape of the aircraft, but we're not going to look at that for this course, okay? So for flight mechanics purposes, it's okay just to look at these terms on the right hand side. So we now have an expression for the velocity of dm. Okay, so v dm, which is an absolute velocity vector, we've got is just equal to the terms on the right hand side. So I'm just going to copy those down to save time. Here we go, this is our absolute velocity vector. So we can immediately get the linear momentum of this part. So the mass of the element is just this dm. So we multiply this by dm, we've got the linear momentum. Okay, so just remember, normal linear momentum, take the mass, multiply it by the velocity, that's how we get our momentum. So we say, I don't know why I switched to red there. Okay, so I'm just going to call the linear momentum dm vdm. Let's switch back to blue anyway. Let's say dm, and then we can just copy all of this down there. dm is just a scalar term. I don't need to include it in the vector. The reason why I'm calling linear momentum dm vdm is because linear momentum sometimes has the symbol p. We're not going to use that because that will cause confusion with the roll rates. And we're not actually using it in the final equations of motion, we're just using it to work out what the angular momentum is anyway. Now we can determine what the angular momentum is, because we said that if we knew what the linear momentum was, we could get the angular momentum from it. So h is equal to r crossed by v dm. Okay, I've got a subscript dm over here just to say that it's the velocity. There's a subscript dm there that isn't over here. That's just to show that we have got the velocity of that small element dm. So the angular momentum of this small element, so we'll say it's dh, belonging to dm, is equal to the cross product of whatever the position vector is of this small part, multiplied by dm vdm, which is the quantity we've got just above. So that is our position vector, xdm, ydm, zdm, crossed with this. It's going to be a nasty cross product to do, just because of, not it's particularly taxing, just because there's a lot of subscripts and my handwriting's sloppy, so let's try and be careful here. So we've got our I, our j and our k components. So our first terms are x dm, y dm, z dm, and then on the bottom I've got z dm q minus y dm r, x dm r minus z dm p, y dm p minus x dm q. Okay, so let's do the cross product. The first row is going to be ydm. I'm checking I'm on the right track here. Yeah, okay. ydm multiplied by ydmp minus xdmq minus z dm x dm r minus z dm p. You can probably see that we're going to have some squared terms here. So I've got y dm multiplied by p, and I've got z dm multiplied by p as well. So we're going to have y dm squared plus plus z dm squared multiplied by p, and then we're going to have some other terms. So I'll do all of the cross product and then we'll bring it all together. So next I'm going to have z dm q minus y dm r minus x dm y dm p minus x dm q. And then in the last one I've got x dm r minus z dm p minus y dm z dm q minus y dm r. Okay, so we said we've always got these squared terms here, so let's just look at the things that are squared. Well, we've got y dm squared, and I've got z dm squared, z, x and x, x, y and y. So we've got squared terms in each row that belong to the terms from the opposite rows, if that makes sense. So in the second row I've got x and z, first row I've got y and z, last row I've got x and y. So we can collect these terms together and we can simplify the expression. So I'm going to end up with p multiplied by y dm squared plus z dm squared, and then the other terms I'm going to have left, I'm going to have minus q x dm y dm. I wish I hadn't chosen two-letter subscript to do here now, but I'm stuck with it and I'm going to continue with it. And then what else am I going to have? I'm going to have minus r x dm z dm. Okay, on the next one I'm going to have q z dm squared plus x dm squared minus r y dm z dm minus x dm y dm p. And then this last one I'm going to have r x dm squared plus y dm squared minus p x dm z dm minus q y dm z dm. Okay, so that's correct. I think that's correct. I haven't checked against what I've done before, but when I go through these, I always check the sort of patterns you can follow just to check that, you know, we're going through a derivation correctly. The square terms here, I've got p, q, and r, which correspond to my x, y, and z rows, and I've got the off row terms. So in the x row, I've got p, which makes sense. I've got y and z there. In the y row, I've got q, and I've got z and x. And in the z row, I've got r, and I've got x and y. Okay, so that pattern follows. And then I've got, in this row, I've got x crossed with y, x crossed with z, y crossed with z, y crossed with x, z crossed with x, z crossed with y. And I've got p, q, r, p, q, r. I've been a little sloppy with remembering the order of how I've been putting things down there, but I've got all of those terms there now. So this is the expression for the contribution to the angular momentum by this small parcel dm. So this whole dirty great expression that we just produced is dh dm. So this is the contribution to angular momentum due to small mass dm at rdm due to aircraft rotation P, Q and R. So now we've got this, we assume that the aircraft comprises lots of little DMs and we're just going to integrate all over the entire aircraft, which is really just a fancy way of adding them all up. Or more, integrating is a fancy way of adding up, the other way around really. So we're going to integrate So if we integrate over the entire aircraft, we can get the entire angular momentum of the aircraft. So h is equal to the integral of dh over a bunch of masses, dm. And if we do that, we've got all of these x and y terms in here. So when we do the integration, we're going to end up with integration over x and y and z as well. I just didn't say that last one. So we're going to get, we've got them sort of split down into three groups here. So I might as well keep it in these three groups. So three sort of columns in here. We'll keep it in those columns. So we get h is equal to P, Q and R, because those are just numbers in here. P, Q and R are just our aircraft angular rates. They can just come out. So we're then going to have the integral y dm squared plus z dm squared dm, and the integral of x dm squared plus z dm squared dm, and the integral of x dm squared plus y dm squared dm. So that's our first term. And they're going to have, zooming out a little bit, I'll see if I can write this small and keep it neat. We're then going to have minus, minus, minus q, r and p. So I'll have integral of x dm, y dm, dm, integral of y dm, z dm, dm, and then I've got the integral of x dm, z dm, dm, and then I've got these last terms which are and then my handwriting's just about okay here, I think. So minus, minus, minus. I've got R, P, and Q. Integral, integral, integral. X dm, Z dm, dm. X dm, Y dm, dm, and then Y dm, Z dm, dm. Okay. Let me just pause 1 second. I need to sort my... Okay, hopefully that's slightly less in my way now. Sorry about that. So, those of you who've taken a solid mechanics class, or those of you who have taken courses with me before in aeroelasticity, sorry, not aeroelasticity, in mechanics of aerostructures, I know that you know what these terms are. So the terms that we've got here are more commonly known as the moments of inertia and products of inertia. So we've got and this is just looking at the integral terms, not the Q's, P's and R's around it. And it's going to be helpful because the big integral expressions with all the subscripts are kind of nasty to keep writing out. So it would be easier if we could just replaces these with terms that we know and we've got other expressions for. And we do, so we're going to replace these with Ixx, Ixy, and so on. So we're going to replace those. Let's just remember how we define these. Our moments of inertia. So Ixx is equal to the integral of y plus z dm. Sorry, y squared plus z squared dm. Iyy is equal to the integral of x squared plus z squared dm, and izz is equal to x squared plus y squared dm. So just remember what a moment of inertia sort of helps us determine. It tells us how difficult an object is to turn around a given axis. So it's a function of the actual pure amount of mass that exists around a given axis. So it doesn't really, mass and how it's distributed. So let's say we've got an object that is of some arbitrary shape and there's an axis going straight through it. So let's say this axis goes through here. If this is our z-axis, then this could be our x, and this could be our y-axis. So then the izz is equal to the integral of x squared plus y squared dm. Okay, or for if we have a uniform density, it would be x squared plus y squared dA, all multiplied by a density. This is then just a function of how mass is distributed. So if I've got mass that exists all around, then I'm going to have a larger izz. So we can see probably for this shape, the way that I've drawn this is something that's flat. Of all of the moments of inertia this can have, izz is going to be the hardest or the biggest for this object, meaning that it's going to be harder to turn around this axis. Okay, so if we've got a big flat object with lots of mass distributed around it, it's going to be hard to turn. So for an aircraft, we can probably intuit that the aircraft is going to be hard to turn around the x-axis because of the wings, and similarly it's going to be hard to turn around the z-axis because of the wings. The y-axis is still difficult to turn around, but it tends not to be so difficult. And so we'll look at some numerical values of these moments of inertia for real aircraft a little bit later. We've also got the products of inertia as well. So products of inertia, these are sort of slightly harder to grasp than moments of inertia. So let's just do a little reminder of what they are. These are Ixy, which would be equal to Iyx, and this would be equal to the integral of x, y, dm. Okay, so it's a measure of, and firstly it's a signed measure. If we look over here at products of moments of inertia, these are always positive. Okay, moments of inertia are always positive. Products of inertia are signed, so because x and y can have magnitude, they, like we say, they can be signed objects. So let's say here, so if I have an object that is sort of arbitrary shape, but mostly axisymmetric, then for this object, my Ixy, well, if we look at if we sort of split things up into 4 chunks, here, 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 and here. Broadly speaking, the IXY in here and the IXY in here are going to have the same sign because I've got positive X, positive Y, and the same here, positive X, positive Y, and then here it'd have the same sign because over here I've got positive Y minus X, and over here I've got positive X and minus Y. So these would be negative and these would be positive contributions, but they'd all sort of these would probably just about cancel each other out. So this would have a low-ish moment product of inertia IXY. If I had a perfectly symmetric body, let's say I've got perfect circle, and my axis goes straight through the center. Then imagine I had drawn that through the center correctly. Then IXY would be equal to IYX, which it always is anyway, would be 0 for this object. Okay, be small for this one. And then if I drew another object, let's say I've got some arbitrary object, but my axis is up here. And for this object, because most of it exists at, let's just work it out actually. Well, actually most of this would be in this chunk here, so it would still be positive because both X and Y are negative in this quadrant, but the largest chunk is taken up by effectively red on here. I guess I'd have a mostly positive IXY. Okay, for that up. So that's just these different objects, all I'm drawing these out, these look nothing like aircraft. The reason I'm drawing them out is because we're saying products of inertia give us an idea of mass eccentricity, or really how well mass is distributed, how symmetric the mass distribution is around a center of mass. Right word isn't really symmetric, we should say how, no, we should say symmetric actually. Okay, so where we've got symmetry, our products are equal to 0, and where we've got asymmetry, then we've got non-zero products of inertia. So the moments of inertia give us an idea of how much moment it takes to affect a change in angular momentum. No, I wrote products, I should put moments of inertia. Yeah, it's kind of clumsy English there, but I've said moments of inertia tell us how difficult it is to add angular velocity to an object. And what I really mean by how difficult, it's how large a moment it takes. In a closed system with no losses, if we've got a product that's got moments of inertia but no products of inertia, once it gets going, it'll keep spinning. Okay, it'll keep going. Products of inertia, on the other hand, tell us how much force needs to be applied, or the moment that needs to be applied to keep something going at constant rates. And they also tell us the net force that's experienced in a non-rotating reference frame due to any form of rotation. Sorry, not in a non-rotating reference frame, I mean in the rotating reference frame. And this last one might sound like it doesn't mean anything yet, but let's think about it. So if I've got a car tire, it's well balanced, right, its mass distribution is perfect, then this would have this is a well balanced car tire. Okay, so if we can imagine that this car tire is made up of different masses all over it. Okay, lots of different masses. I've drawn 4. Really, it's made up of as many different masses as you can afford to draw, or particles that we've got in here. Each of these is going to have a force, tension field holding the whole wheel together. Each of these is going to have a force. Fc is equal to dm omega, wherever they happen, or omega squared, wherever they happen to be due to rotation. But all of these forces are going to balance out if the masses are symmetric, or in this case, if the axis symmetric around the center. Here's a different case where we've got a second car tire. Okay, we haven't quite got the axis in the center, and we've also got, someone's put a balancing weight on here. So we've got these masses which are all in conjunction. When we spin around, we get no net force. This one that is unbalanced produces a net force as we spin this wheel, and you can experience this. I'm sure you've all played with things that spin in your life. When they're unbalanced, they've got this force that you experience as being periodic because you're holding it and you're in the inertial fixed reference frame, or you're in the non-rotating reference frame, I should say. But in the rotating reference frame, there's a constant force. Okay, so for our aircraft, if our aircraft has a large product of inertia in a certain axis, that means that when we spin it, we're going to experience a net force within the aircraft. So after that diversion about talking about those, I think it's important to talk about these because it's not always intuitive what products of inertia are. They're just a measure of how symmetric a body is, or how symmetric the distribution of mass around a certain body is. So we've got those there. With those definitions, it means we can take this equation. Let's take this out because I'm never going to get to write around this again. Let's zoom out. And I'm going to come down here. So now we've got this, we can then just replace all of these terms. So this is Ixx, Iyy, ixy, and then I've got ixy, ixz, ixz, iyz, ixy, iyz. So we can rewrite this now without the integrals in there, which is handy. So we can say that the total angular momentum defined in the axis system of the aircraft, so this h is still in body axes, is equal to p ixx minus q ixy minus r ixz, q iyy minus r iyz minus p ixy r ixy minus p ixz minus q iyz. Okay, so we're almost there. We're almost there, okay? We can just have a look here. Let's just look at the positive terms. So we've got positive terms with P, Q, and R in each of these. And in each of these, we've got the product, sorry, the moments of inertia, Ixx, Iyy, and Iyxy. That's incorrect there. That should be Izz. This, nonsense. That's Izz. That's my own stupidity there. Okay? Yeah. I caught that. It's probably the first mistake I've ever made. There are a few times that I've really messed up with a mistake that I almost can't believe I've made, and I've just had to stop recording. And I've been keeping each of those I'll say swear-filled rants every time I finish one of those, and I'll just put them all together into a nice video at the end of the semester. Okay, so I could then write this as P, Q, and R. That'll be handy because that's just our rotation vector, or sorry, our body rate vector. So I know that my diagonal terms are going to be Ixx, Iyy, Izz. So I'm going to have up here minus Ixy. Let's see if I can move that over. No. Let's make better use of this large matrix space that I've drawn there. Okay, so P, I've got minus Ixy, and then I've got, for the R term, I've got minus Iyz, and then for P down here, I've got minus Ixz, and then I've got here, the Q term, I've got minus Iyz. So handily, this matrix on the left already has a name, it's called the inertia tensor. So this is equal to I multiplied by omega vector, which is the rotation vector. So we've got these two things. This is the inertia tensor, which just contains both our moments of inertia on the leading diagonal and the products of inertia on the off diagonal. And then this is my body rate vector. Okay, so we're almost there. We're almost there. What we need to do is we need to determine the absolute rate of change of angular momentum. So here I've got, this is the the angular momentum of the whole aircraft defined as a product of the inertia tensor and the body rate vector due to aircraft rotation. Now this is defined in aircraft body axes. So I need to put this into the Coriolis vector to determine the time rate of change of the angular momentum in the inertially fixed axis system. Sorry, the inertially fixed reference frame. Okay. So before we do that though, we're gonna clean it up, because if we go straight in with this, we're gonna end up with a whole lot of terms that we don't really care about. So we're gonna look at the inertia tensor. Okay, and we're going to rely on some symmetry of the aircraft to help us out. So we're going to think about the products of inertia. So all of these are equal to all of these. So there's only 3 of them we need to look at. Okay, we're going to see which ones we need to care about and which ones we can get rid of. So let's draw our aircraft out. So the way to remember about which sort of axes they refer to is the letter that's not written is the axis around which we are looking for symmetry. So IXY refers to the aircraft z-axis, so we can look at a crudely drawn aircraft. Okay, IXZ, so I'm now looking around the aircraft. And then for this one, looking around the x-axis, so let's say so what we're looking for in each of these is we're looking to see roughly how symmetric the aircraft is around these 4 quadrants. So I'm going to draw some dots on. And let's say we've got 1, 2, 3, and 4. Now, the aircraft, as certainly as I've drawn it here, is pretty much shaped like a cross. So we're going to say that IXY, which is equal to IYX, for our purposes and for aircraft flight mechanics, fixed wing aircraft, pretty much equal to 0. Okay, this one here, probably can't get away with saying that. Okay, so we're going to say that IXZ is equal to IZX, and that's not equal to 0 for our case. So we're going to have to keep this one in there, and then pretty easy to see that we've got quite a lot of symmetry around this axis as well. So we're going to say that IYZ is equal to IZY is equal to 0 for our case. So we got rid of these. Okay, so we've just done what's called simplification of the inertia tensor via symmetry. I know sometimes it seems like I'm just making this up when I go along, and it's it's my idea to get rid of this. This is what we do in fixed wing aircraft flight mechanics. We assume that some of these products of inertia are small by contrast to others. It's not going to be the case for all aircraft. You might have a given aircraft in which you've let's say some aircraft, say you've got a big delta wing, canards at the front. Horrible canards just drawn. This looks like a ghost wearing a dress. For an aircraft shaped like this, you probably can't get away with assuming that IXY is equal to 0. So remember the the Rafale, or a ghost in a dress. You probably can't make this assumption for it, okay? And you can make similar justifications about not making this assumption for other aircraft. Okay, so for this one, you probably end up saying that IXY is equal to IYX is not equal to 0. Okay, I don't know whether during the design of the Rafale, Eurofighter, other fighter aircraft with big delta wings, whether that was included, but I'm making a guess that for certain aircraft planforms like that, you can see there is not a symmetric, or there's not the quadrant cancelling out of those contributions to products of inertia. So we're going to go back over here and we're going to simplify our inertia tensor. So with our simplified, inertia tensor, we can now write H is equal to Hx, Hy, Hz. That's equal to our new svelte inertia tensor. We just lost we lost 4 terms out of it, which is pretty cool. Multiplied by our rotation vector, P, Q, and R. Sorry, our rate vector, not our rotation vector. So we can then multiply this out and get the different terms for it. Let me just see if I can do it without. No, I do need to do this. Made a mistake there, didn't I? No, I didn't. No, I didn't. I made a mistake there. Okay, so this is my angular momentum vector on an aircraft, subject to the assumptions that we've made, which is that it's symmetric in certain axes and that we can look at the, well, we assume that it's rigid as well. So we assume we've got a rigid aircraft. This gives us our inertia tensor for this aircraft, but it's defined in aircraft body axes. So thus we need to use the Coriolis identity to give us the total time rate of change in inertially fixed axes, or in an inertially fixed reference frame. And let's just remind ourselves why we're doing this, just in case you've forgotten. So we're looking for the absolute time rate of change of the angular momentum vector, and the reason we're doing that is because once we've got it, this is equal to sum of the moments. And once we've done that, we've got our rotational equations of motion. And once we've got those, there's just a little quick exercise we need to do in working out the relationship between our rotation vector and the Euler rates, and then we're fully able to describe aircraft flight in 6 degrees of freedom. Unconstrained flight in 6 degrees of freedom, I should hasten to add. So let's do this Coriolis thing. because it seems like the point we should do it. So remember, h is equal to I omega. So that's going to help us out here. We're going to say we use the d I omega on dt xyz plus omega crossed with this expression here, which is okay. So let's just see. I like having a canvas I can scale around and do different things to. I hope it doesn't give any motion sickness. Maybe I hope it does. Okay, so because we've got two terms in here, we should really use the product rule to go through this. So we'll say that's d I omega on dt of xyz is equal to d I on dt of xyz multiplied by omega plus d omega on dt of xyz. Because we've assumed a rigid aircraft, this goes to 0, which is handy. So we just end up with our inertia tensor multiplied by the first derivative of the angular rates. So that's okay, so we've got that, that's handy. So we need to do that cross product. So we don't need to do a cross product, we've got a multiplication to do, and we know what it's just going to be. It's actually just going to be this expression here. Let's see if I can turn that to green. That would be cool if I could. No, I don't think I can. I was wanting to see if I could change the colour to green. No. I don't need to play with this any longer than I already have. Okay, so let's say it's going to be equal to that. I'm not sure why I'm writing in red. With dots over my rates. Okay, so I've got my first term. That is the first bit here, and then it means I need to do one cross product. So dh on dt abs is equal to this bit. Okay, that's my first expression, and this cross product, I'm going to do this over here. So we've got I, j, and k, p, q, r, ixxp minus ixzr, iyq, izzr minus izxp. So this equals, I don't know how you guys are taught how to do cross products in America. I don't know, but I draw them like this, and I put my thumb over the line that I'm supposed to be collecting, and then I do the cross products, and just remember to flip it over for the center one. But the expressions that I end up with here are q izzr minus I zxp minus r q I yy. Yep. R I x z r. No, let's not do that. Let's do ixxp minus ixz r. I might end up speeding through this so that my voice will end up sounding ridiculous when I do this later, but that's sort of funny. Okay, so that is my cross product. Let's bring this down. Haven't learned my lesson, I kept it in a different colour. Let's write this out in one big expression just for the hell of it. Okay, so we'll say my absolute rate of change so h dot absolute is equal to hx dot hy dot and hz dot. In general, when you see a dot, that's denoting an absolute time rate of change. And that's equal to so we've got these first terms which I've put down in blue, and these exist due to the moments of inertia and accelerations about the axis corresponding to the row that we're talking about. Then I've got some other terms which I've got Q and R here, and those are related to gyroscopic precession. So QRI ZZ minus QR IYY, and then in the second one I've got IXX and IZZ with P and R, so I've got plus PR IXX minus IZZ. And here I've got PQIYY, PQIXX. And then I've got the other terms that I've got left. I've got this one over here, I've got a product term. So these are still, you'll see these are still moments of inertia. Okay, they're just moments of inertia corresponding to other axes. And I've then got products of inertia. So I'm going to have, they're going to be a minus term. All of these are going to be minus terms up here actually. So my iPad responds, that would be nice. Oh, I've crashed the app that I was working in. Wonderful. Let's hope that it saved where we were up to. Things happen when I've been working on a document that's become a little bit unwieldy, and I haven't saved in a while, or I haven't started a new thing. So let's see if we can continue with this, and I'll remember to not continue from previous lectures and to start a new one. So those terms are just brought down. Those were these terms due to products of inertia, moments of inertia that belong to axes other than the one for which the row of the matrix we're looking at. Okay, so this has got, I've got products of inertia with moments of inertia IZ and IYY, even though we're in the X row here. I've then got RP IXX minus IZZ. I know I've already done this, but rather than copying it down, I'd rather just go through this again. I've got these two here, so I've got PQ IYY minus IXX. Let's just do a quick save. So the remaining terms that we've got are anything that involves a product of inertia, and I'm going to draw these in green. This first row is negative, the next two are positive. So here I've got minus IXZ R dot and minus RXQ. No, not I haven't got that one. I've got this one here. So I've got minus IXZ R dot. It's going to be R dot plus PQ actually. So Q here as well. Okay, in this next row, I've got this one here and this one here. So I've got RP, and I've got, is that P squared? No, it's R, sorry, it's R squared and P squared I've got there. I'm completely missing. So it's R squared here and P squared. I can't quite read my own writing here. So I've got plus IXZ. So I've got P squared, which is positive, minus R squared, which is negative, because it was a negative sign over here. And then in this last row, I've got IXZ. So I've got RQ minus P dot. Okay, so these first terms are in blue. These correspond to an increase in angular rates corresponding to the axis about which we are applying this force. Because remember, these are equal to L, M, and N, which are aerodynamic moments. So these first terms are pretty obvious. These are sort of the easiest ones we've got. So this is an increase in angular momentum due to a change in angular rate about that axis. Okay, so for example, that would be an increase in the angular momentum around the roll axis due to an increase in roll rates. These here, these are gyroscopic precession. And these last terms here are coupling terms. So these gyroscopic precession terms, we can see they occur, and in each case, so for the X row, the whole first row, we get an increase, or we get terms related to the rolling moment of inertia, or the rolling angular momentum, we get an increase in the rolling angular momentum due to the difference in moments of inertia of the other two axes. So if the other two axes have got equal amounts of moment of inertia, these terms disappear. Same for the second row, same for the third row. If the other two axes have got the same moment of inertia, these terms disappear. Some textbooks like to go through and try and make sense of these. I don't like the methods they go through to try and make sense of them, because they look at things like in a pull-up, then rolling, you experience a yaw rate. For one, the examples that I've seen where they go through these, I don't like these, because one of the examples said, consider IYY to be big and IZZ to be negligible. And that's nonsense, okay? Because IZZ, and I sort of went and checked in a bit of a, I went and had a check online myself. I thought, oh, that doesn't sound right to me. Let's go find some general aircraft data. I thought that IZZ is in general going to be bigger. And let's see if I can confirm what I found. Okay, so we got there in the end. What I'm trying to show here is that in general, for all of these aircraft, this is, I just did a search for, this is coming up for some flight simulator page, but in general, it's normally a good source of aircraft data. By comparison, for all of these aircraft, they've all got, so we've got an F-16, F-4 Phantom, C-172 Skyhawk. All of these have got a larger IZZ than they have IYY. And that makes sense, because you'd expect your aircraft to be harder to turn in yaw because of the fuel stored in the wings and the fact you've got these bloody great wings hanging out, than it would be in pitch. So one of the textbooks, whose name I won't name and shame because that's unprofessional of me, I don't, unless I've confused what he's trying to do, I don't like that they look at these and try and then compare some of these gyroscopic terms back to this first order behavior. Because the whole point of deriving these equations is that we can look at the coupled response of the aircraft i.e. if I've got R and P, then that is rolling and yawing rates, and then that's being given in response to a pitch moment. So I'm also getting pitch rate out of that, and I'm also getting P and R here in terms of squared terms in relation to this product of inertia. So this is a whole couple set of equations that actually you can't really look at them in isolation, because M is going to be changing in response to anywhere that I've got a Q in these as well. So I don't like the idea of looking at these in isolation. Basically, we've derived them in order to develop the full aircraft equations of motion, which include these, so we can have appreciation for what these are. Gyroscopic precession terms, they are an increase in an angular rate about an axis corresponding to a moment that isn't that axis, basically. So we can see here we've got R and P, which is roll and your P and R, which is roll and yaw rates, is going to be somehow related to the pitching moment if and only if the two moments of inertia, so this is the rolling moment of inertia and the yawing moment of inertia, are different. Okay, that's a complicated expression, complicated to deal with. Don't lose yourself too much in trying to make sense of the sign of these, because it's all going to be dependent on the different sizes of these moments of inertia. These coupling terms here, we can think a little bit about what these mean. These are effectively, like we said, it's due to that mass asymmetry of the aircraft, and we can see that some of them, we've got terms that exist due to angular acceleration, and here we've got an angular acceleration due to r dot, so that's the yaw acceleration. We've also got the cross product of pitch and roll rates, and then this is in response to an aircraft rolling moment. You probably appreciate there would be a whole lot more of these. That we've actually got this sort of weird mishmash of them. We've got some squared terms in the center, and we've got dots and RQ and PQ here. We've got far fewer of them because we simplified the inertia tensor. Okay, so let's. God, no wonder this was having trouble with this page. I've produced an enormous unwieldy vector diagram here. Starting right back here, let's just remind ourselves where we started. So we actually started at the translational equations of motion, saying that we developed these by working out what the absolute acceleration was. The absolute acceleration is a product of this this first time derivative of the absolute velocity and the cross product due to the Coriolis identity, which we actually derived, which is pretty cool. And the right hand terms is these non-conservative forces. We then said, look, we'll try and do the same thing for rotational motion, so we need a way of talking about that. So the rate of change of angular momentum is equal to the sum of applied moments. So we needed a means to talk about angular momentum. So we said if we could come up with angular momentum defined in body axes, we could get the absolute rate of change using this Coriolis vector. So we had a look at this. We said angular momentum is equal to whatever the linear momentum is, and the cross product of that with the distance from our axis. So rather than trying to tackle the aircraft at a whole, we said let's split the aircraft up into a series of masses, and then we're going to work out first off what the translational velocity of that dm would be if the aircraft's got P, Q and R roll, pitch and yaw rates. Once we've got the velocity, we can easily get the linear momentum, and then once we've got the linear momentum, we can use that relationship, that cross product with R, to get the change in the angular momentum of that small mass due to P, Q and R. We're then going to write these out, and then we saw we've got a bunch of terms here that are y squared and z squared and some products. So when we integrate those, these are just our moments of inertia. Moments of inertia refer to how difficult an object is to turn around a given axis, or to get it started. So like a big flywheel has a big moment of inertia. A long thin cylinder has a low moment of inertia around that principal axis. Then spent a bit of time talking about products of inertia, because I don't think you'll have necessarily thought too much about what these mean from our other courses. These just tell us how difficult something is to keep going. Okay, so if we've got a high moment of inertia, once we've got something spinning in a system with no losses, it'll keep going. If it's got a high product of inertia, then it won't keep spinning around that axis, because it will lose rotational speed as soon as you stop applying that torque. So they give us an indication of the torque required to keep something turning, and also the net force inside a rotating object. So I had that analogy with a balanced tyre versus an unbalanced tyre. Then, once I was done waffling on about that for long enough, we said, well, we'll use that definition to take our inertia tensor, and then we'll simplify it by looking at different aircraft shapes, mainly looking at these sort of traditional fixed wing aircraft shapes here. And then I drew this terrible attempt to draw some sort of canard fighter. So if you have a ghost in a dress, then you probably can't say that your IXY is 0. So we've got our simplified inertia tensor. We could write out then the angular momentum of the entire aircraft in aircraft body axes. And then I thought I'd made a mistake there, but I hadn't. And then I said, we know that once we've got that, if we put it into our Coriolis vector, what we're going to get is the absolute time rate of change of this, which is equal to the sum of the moments. I thought that equals was following here. It wasn't. It's just an arrow up from down here. So we do that. I then jumped all about the page, saying, well, actually, we need to be smart. We need to see, really, I need to look at this with the product rule. And then we assume we have a flexible aircraft. Sorry, not a flexible aircraft. We assume we have a rigid aircraft. So that is equal to 0. The time derivative of the inertia tensor is 0. And then we're left with these terms here. And then I separate these out into these sort of direct terms, which give us an increase in angular momentum due to an increase in a rate about a given axis. We've then got these terms due to gyroscopic precession, which are the product of angular rates off an axis and the difference in the moments of inertia about those other axes. And then we've got these coupling terms, which there are fewer of them than we might have had we not simplified our inertia tensor. And I will, again, I give a bit of a warning about this. I normally say try and understand things and try and go through them. Don't spend too much time trying to think about the actual significance of what these mean, other than we can see here that when we apply, because this is equal to L, M, and N, this is our rolling moments. We can see here that if we've got an aircraft that has IXX and IYY being different, which it will, when we have both say if we have a pitch rate and a yaw rate, that will be affected as a moment in the roll axis. This gives us a coupling due to gyroscopic precession, or more, I should say, if we've got a pitch rate, if we have an increase in L, we'll see an increase in R. Okay, so don't think too much about these, because I've looked in a few textbooks of ways they try and intuit them, and I just don't like it, because this is a coupled system and we develop these coupled equations such that we can use them as a whole. In static stability, we want to think about that sort of first order aircraft response. We're going to take these and do something smart with them by looking at them as a system, and then that's going to enable us to determine the aircraft response. We're sort of beyond the point where we can intuit too much about these behaviors without doing some complicated mathematics and ending up with things like the characteristic equation of the system. So that is the translational equations of motion determined now. That is what these bad boys are. Okay, we've got the translational equations of motion. We've got these are the translational equations of motion. Those were the rotational equations of motion. I do wonder how many of those mistakes I make and I don't hear myself make them. Rotational equations of motion, the ones pertaining to rotation. Translational equations of motion are the ones pertaining to translation. Okay, We've got one more set of things we need to do, and we're going to do that. I'm going to record a quick lecture tomorrow, and that is basically, if we want to look at the aircraft position at any one point, then we know the aircraft position is given by its position vector. So we've got x, y, z, and that would be defined in Earth axes. So we'll say RE is equal to XE, YE, and ZE. That defines where it is. If we want to define the aircraft's attitude, then that's defined by the Euler vector, which it can be given the symbol psi. Should be an uppercase psi, but I'm not very good at drawing that. So let's say like that. That would be the Euler angles, which are phi, theta, and psi. Remembering that the way that we need to apply these are actually to go from Earth to body to yaw, pitch, roll. So it's not in the order we've got them up there, it's in the reverse order. To look at how the aircraft attitude changes, it corresponds to the time rate of change of these, is going to give us the Euler rates. So we'll say Euler rates, we've got now, remember that the Euler angles give us an attitude. You might think, well, can I take my transformation matrix and compare this to my body angular rates? Because we've got rates, and we've got body axes, and we've got Earth axes. In effect, it would be t minus 1, because it would be the inverse to go this way, remembering that the transformation matrix we defined took us from Earth axes to body axes. No matter how I write that, we can't do this anyway. Okay, we can't do this because the transformation matrix takes, so T does Earth to body, T to the minus 1 does body to Earth. And these here, these ain't defined in Earth axes, okay? Psi is defined in Earth axes. Theta is defined in intermediate 1, and phi is defined in intermediate 2. So we need to do a slightly different approach to come up with two transformations, one of which is going to go between body roll rates and Euler rates, and the other one's going to go between Euler rates and body rates. Okay, it's not an orthogonal matrix, annoyingly, but I'll give you the inverse anyway. So we'll spend a little moment of time going through and just coming up with the two sets of equations that do those transforms for us, and then we've derived our full sets of equations. It's 12 equations that fully describe unconstrained aircraft flight in 6 degrees of freedom. I say 12, it's actually only 9, but because we've got to have both forms of this relationship, basically the relationship that goes between the Euler rates and the body rates, and it's just easier to present it with the matrix in both forms. We'll say it's 12, and it sounds like we've done more work than we actually have. So we did a lot today. We've covered the rotational equations of motion in one bloody great lecture. I'm sure there'll be questions about this, so I look forward to seeing them on Wednesday. Put them on Slack, put them in the comments, do whatever. This is a lot of fun. I really enjoy this stuff, and I look forward to learning more about aircraft with you guys as we go on. So that sort of website that I found that's got the inertia tensors for different aircraft, you can also find stability derivatives for different aircraft. So I would like you guys to start looking up stability derivatives for different aircraft types, and I can start using some of those in examples in class if you give them to me with enough time, okay? Because we're going to use those to look at the actual stability characteristics of different aircraft. So find them for me and we'll go through them, okay? Hope you've all had a wonderful long weekend, and I look forward to seeing you guys later in the week.